You might notice that there's an arrow here that says EAF. EA, that's our new thing, activation energy. And this activation energy, F, is the forward direction. Activation energy, forward. What's very new for you is the fact that we have an energy of activation in the reverse. So if I was reversing the reaction, it would be not endo anymore, but exo. It would have this much activation energy. It would release this much energy. So we are going to talk from now until forever about forward direction and reverse direction for reactions. Some don't go in both directions. It's not a guaranteed universal, but some do.
Patrick Davis, the office, please. Patrick Davis, the office.
Good. So we're going to talk about delta H the same way we always did. Delta H does not change. The only thing that we need to measure that's new is this forward activation energy and the reverse activation energy. You can still, for this time, think about it as how much did I put in and how much is coming out. So if I get out more than I put in, it's exo. And if I put in more than comes out, it's endo. So everything still follows mostly the same pattern. We're going to write an equation that helps to express this. Activation energy forward minus delta H will give you the activation energy in the reverse. This can also be written as activation energy forward is equal to activation energy reverse plus delta H. You can rearrange that equation in various ways, but it will help you solve your problems. Then for this one, I'm only going to write one version. You can obviously, oops, this is forward. You could obviously rearrange this one as well. So it's pretty basic integer math, but we just want to make sure we understand where it's coming from. Activation energy forward will equal your delta H plus your activation energy for this endothermic reaction. It's actually going to be the same here, except for your H is negative. So the reason that it's the same here is because in this case, delta H is negative. So you have to pay attention to delta H. Is it an increase or a decrease? And that will make the equation correct. So the forward is equal to reverse plus delta H. That's always true. Just delta H is sometimes going to be negative. Next, we're going to talk about the effect of a catalyst. A catalyst, as you know, is involved in increasing the rate of reaction, which is why we're talking about them in our rates unit. A catalyst is not actively reacting in a reaction. It's not technically a reactant or a product. It goes into the reaction and it comes out the same way. So if you remember grade 11 chemistry, in our second last lab, we used magnesium dioxide in the lab to liberate some oxygen from hydrogen peroxide, and the oxygen came out, and we said that that black powder wasn't used up in the reaction at all. It was actually a catalyst to create the reaction. So this is a catalyst. A catalyst lowers the activation energy. I hope these diagrams are helpful to you. When you have no catalyst, your activation energy is hump to hump, and your hump is lower. Your activation energy is lower. So what I'm going to say is exactly just that. They are chemicals that increase the rate of reaction by lowering the activation energy. In contrast, an inhibitor is going to raise the activation energy. So inhibitors work in this context. You can use inhibitor differently in medicine, although some work in a similar way. For a chemical reaction, an inhibitor is going to slow the rate of reaction, which we want to do in many cases. We don't always want a reaction to go quickly. The difference between a slow burn and an explosion is often just the rate that something combusts at, right? But there's lots of other cases that we've talked about. So an inhibitor is essentially, in this case, the opposite of a catalyst. It's going to be a chemical that decreases the rate. By raising the activation energy.